We now have example 4.2-1, length of tubing for cooling coil. A thick-walled cylindrical tubing of hard rubber having an inside radius of 5 millimeters and an outside radius of 20 millimeters is being used as a temporary cooling coil in a bath. Ice water is flowing rapidly inside, and the inside wall temperature is 274.9 Kelvin. The outside surface temperature is 297.1 Kelvin. A total of 14.65 watts must be removed from the bath by the cooling coil. How many meters of tubing are needed? So let's try to sketch this problem first so that we can have a good look or grasp on what is the problem really is all about. Okay, we have this set up here. This is really oversimplified. Supposed to be there must be like something like coil, right? That this must be coiling. So more or less it looks like that, but it's very hard to study that. Let me just focus on a single no, this one. This really the actual like the tubing that is being placed in this bath, but I'm simply oversimplifying it into a straight tube so that it's easy to work with. And in this case, fluid actually enters to this. This is cooling water and flows out through that. And since this is hot, this yellowish or orange solution is or bath is hot and this is cold, heat will flow inside. Okay, heat will flow from the bath towards this ice water, which is cold, and conduction happens into this black portion here. Like heat will flow through the cylindrical wall inside from the outer surface of this tubing to the inside through this so that heat will then be transferred to this liquid, blue liquid here. So now let's analyze this one further. Okay, we have here like a cross section of this, like the heat will flow from the outer, okay, from the liquid here through this wall and supposed to be there, and similarly through all of this surface, because this tubing will be opposed into that. Okay, so in almost all direction, okay, radially inward. Okay, heat will flow radially inward to that. Now the thing here is a very simple lang yung approach natin. Okay, since ang equation lang dito will just be this. Q is equal to the what? Driving force delta T over what? The resistance to flow. Very simple. The equation looks very simple, very compact. And Q here, meaning the heat that must flow, Q must flow into this, through this wall, will just be equal to 14.65 watts. Watts means what? Joule per second. That amount of heat must flow per second into that wall. And then, delta T, well, the temperature here on the outer surface, we call that TO. In this case, TO is equal to what? The outer, okay? Like this is TO here, at the outer. TO is just equal to, well 297.1 Kelvin. It's higher than the temperature of the um, TI here, temperature of the inner radius of the pipe. Okay, and that is, well, the TI in this case is just equal to 274.9. 274.9. Okay, which means here that delta T will simply be, well, the difference in temperature, 297.1 minus 274.9. Okay, delta T will just be equal to 22.2 Kelvin. That's the driving force, okay? This is, now the only problem perhaps that we'll have is how to find the resistance. Q here, in this case, is 14.65. Let me put that here. 14.65 watts. Okay, wait. Perhaps the only thing that we'll have a little bit of difficulty will finding the resistance. In this case, we know that the resistance that this rubber tubing will provide will just be, well, the thickness of this. thickness, so meaning the bigger the thickness or the thicker the tube, the higher the resistance to flow, right? Because the heat will need to pass through that quite a distance. In this case, that's delta R. Okay, delta R. And what else? Well, it's also inversely proportional to the conductivity. The higher the conductivity, the resistance, the smaller the resistance, and also with the area. Okay, meaning the bigger the area where heat could flow, the smaller the resistance will this one will offer. In this case, when we say area here, since we actually have heat will flow through variable area, at the outer surface it's quite a lot of surface, but as the heat flows inward, the surface area where it flows, or the area where it flows actually becomes smaller and smaller. In that case, we mean here lag mean, area lag mean. So let's now try to compute or put values to this case. So what is delta R? Delta R will simply be, let me just put quantities, values to this quantity. Delta R, R outer minus R inner. So R outer is what? 20 mm. So 20 mm minus 5 mm. So delta R, or the thickness, is just equivalent to 15 mm, or that's actually, this is mm. Okay, 15 mm. Or that's 1.5 times 10 to the negative 4 meters. The conductivity K is normally the problem in here. We need to find for the conductivity, but since the book gave us from appendix 8.3 the thermal conductivity, and if in the board exam perhaps if this will appear, we just hope that if it's not given, then you could look it up in Perry to look for the value of the conductivity of this hard rubber. And in this case, it's given to us. It's equal to 0.151 watts per meter Kelvin. Okay, and the last thing here will be, well, what will be the area log mean? Where area log mean is just equal, right, to the outer minus area inner over ln of area outer over area inner, right? And actually it could be interchanged. Either you put the inner first or the outer next, as long as you'll be consistent with the what to put first and what to put next. Either this one will be interchanged. Now, what is area outer? Well, AO will simply be, AO will just be 2 pi RO times L, right? Where, of course, R will be the outer radius, this one, this radius we're talking about. And L, we don't know yet L because it's what we're looking for. We're looking for what will be the length to be able to provide this heat transfer, okay? And of course, L here will be a variable. RO, we know that that's equal to 20 mm. And how about AI? Similarly, AI will be 2 pi Ri, the inner circumference times the length, which we don't know yet. So the moment, that's L. That's the length of the pipe, the total length of the tubing. Okay, and we put values to this, substituting this in standard, 20 mm is just, what, 20 over 1000 to make it 2 meters. So let's do that, and I put values to this directly, okay? I'm putting values to it, and that will lead to, okay, the outer area, when we do the math for this, we substitute values for the outer radius and the inner radius, will give us 0.1257 L. Well, L is the length of the tubing, and AI will be 2 pi RIL, which is 0.0314 L. And substituting that through here, as you can see, area O over area I, L will cancel, and putting that AO minus AI, area log mean will just be then equal to this one. Just direct substitution will then, the L and the L cancels in the denominator. This will then lead to 0.068 L, 0.068 L. So the area log mean is simply 0.068 L, which has of course a unit of meters squared because this is an area. Now we can now directly or compute for the resistance R. In this case, putting the value delta R, thickness will just be 15 mm or 15 divided by 1000 meters. Putting in the K, and the area log mean we'll then be getting, okay, we're getting this 0.015, which is just a thickness in meters, 0.151, that's the conductivity, and 0.068 L, that's the area lag mean, and that will lead us to a resistance of 1.461 over L. The unit of this will be more or less, well, delta R is in meters, this will be watt per meter Kelvin, and this will be in meters squared. Essentially, the unit for this will be, anong matira? Well, matira will be 1 over, the denominator will be W, and we'll have meters squared, and then we still have Kelvin. Essentially, that's it. Now, we're now ready, I believe, so never mind the units. I know that we can check that out if we put that here. More or less it will cancel. Now, the thing is, wait, I think there's a problem with the units that we have. This is, I get confused with the meters and the Kelvin. It's in the denominator, so let me clearly put the units. Okay, delta R will be in meter, K will be in watts per meter Kelvin, and the area will be in meters square. Essentially, what will we have? Well, we'll have K over W, right? Okay, the resistance will have a unit of 4 of Kelvin. This will turn out to have a unit of Kelvin per watts. Okay, so in this case now, let's now put that into here. And in this case, we'll be having a resistance of 1.461 over L. The unit is Kelvin. Kelvin per watt. Okay, the Kelvin and the Kelvin cancels. The watt will be placed in the numerator because it's the denominator also in here, and the watt and the watt will cancel there. And it will lead us, simple math, will lead us that the length of the tube, this one, will supposed to be, okay, no, I'm not really doing the math here, L, if we do the math here, L will just then be equal to, the length of the tubing must be equal to 0.964 meters, okay, by, doing the algebra for this. So, which means that we need to have a tubing, a minimum of 0.9, close to a meter of tubing, so that we could what? Remove 14.65 watts of heat from this bath. It can be removed by this cooling water or the iced water that is flowing through this tubing. And hope that you find that even if I had really a messy solution to that, I hope that you still find order amongst this chaos. Thank you.